Hello everyone, and welcome to my online tutorial for Mechanics 1. My name is Kevin. I am currently a master's student at UOIT. I'm a candidate for a Master of Science in the Science faculty, obviously. And today I'll be talking about a very simple subject regarding vector notation. Then I'll be talking about dot product, cross product, some projection, and then I'll work on an example for you guys from the textbook. So why don't we get started? I'm sorry if I know this is very basic stuff, so I apologize for anyone who is more advanced, but this is a second year course, and I don't want to scare all of you, so let's talk about vector notation and the dot product. Okay, so let's say we have two vectors here. So let's say we have a vector A and a vector B, and they have some angle in between them. Okay, so in my little 2D coordinate system, that's supposed to be perpendicular here, that's supposed to be horizontal, and this is vertical. So I have my little x and y axes. So the way I write my vectors is with lines underneath them. This is totally equivalent. So this means equivalent if you didn't know. This is totally equivalent to with a little arrow over top. It's just the way I like writing my vectors. And it is a little bit of peer pressure from my professors from undergrad because they all used underbars as well. So basically, when you write down a vector in a 2D system, this can just be written as the components. So this would be the x component of A multiplied by x hat, so the direction. So this is the unit direction for that vector in the x direction, and then we have a y hat. Oops, sorry. And this is also equivalent, so if you haven't seen x hat or y hat, which is just a unit direction in the x and y direction, it also sometimes can be written as I hat or j hat. So this just tells the direction, and then this gives the magnitude of in the certain direction. Okay, so a little bit more about these unit vectors. So we have x hat, which is equivalent to I hat, equals 1, 0, 0. So as you can see, when you take the magnitude of either I or x, or whatever you want to call it, x hat or I hat, you can see that this vector here is just 1, 0, 0. So when you take the magnitude or the square root of the individual squares for this vector, you get a length of 1. So I'll go ahead and write down the y as well. This is equivalent to j hat above, which equals 0, 1, 0. So again, you can see that the magnitude of this vector here, or y hat or j hat, is also equal to 1. So it just tells you the direction of the vector. So now if we're working in 3 dimensions, then we'd have the z coordinate. So if we have z, then we would have the z hat equivalent to k hat. So a lot of the time you'll see k hat for the z direction. And this is equal to 0, 0, 1. I noticed in the textbook for this course, they also used little e's. So they'll use like little e, I. So this is just if you have an arbitrary vector or an arbitrary coordinate system, these EIs just represent the unit for the different coordinates, so the unit vector for each coordinate. Okay. So a little bit more about these unit vectors. So we have I, J, K. They are direction vectors where the magnitude of the vectors, the unit vectors, are always 1. So the magnitude of a vector is simply just, it looks something like this. So you put these bars around them. Sometimes it's absolute value, sometimes it's the norm, the Euclidean norm for this vector. But it's always, sorry about that, always equal to 1. Okay, so now going back to our vectors that I drew above here. So, okay, so now we have A and B. We have A, which equals the x component times x hat plus the y component times y hat. Right now I'm only dealing with the 2D vector, so 2D system. And then we have our B vector, and that has an x component times x hat. And then it also has a y component times y hat. So this is the exact same as writing ax, ay. And this is the exact same as writing bx, by. The y hats just denote the x, but the x and y hats denote just the coordinate system that we're working in. So we're working in Cartesian coordinates, we have x and y's. Okay, so I'll form a new page here. So if we wanted to find the dot product between these two vectors, you just use this formula here. So we have the magnitude of A times the magnitude of B cosine theta equals A dot B. So this dot, when you're dealing with vectors, is different from multiplying. And this is maximized. So the dot product is maximized when, when theta equals 0. So if theta equals 0, then cosine is 0 equals 1. Which is something you guys all should know. Okay, alternatively, I think the textbook may write it like this. So alternatively, you could write A dot B equals the sum of I equals 1 to n, where n is the dimension of the vector, or of the vectors. And then we have the individual components multiplied by one another and then summed together. I don't know where that came from. Okay, so these AIs really just stand for AX, AY, AZ, BX, BY, BZ. So let's see an example of the dot product. So we have an example. So let's say we have two vectors in a two-dimensional system. What is the angle between them? So we want to find what is the angle between A and B? Question mark. Okay, so here A equals -6x hat plus 8y hat, and B equals 5x hat plus 12 y hat. Okay, so how do we approach this problem? We know from the formula here that I mentioned before, all we need to do is we need to find the magnitudes of the vectors and then just the dot product between them. And once we have that, we can divide the dot product by the magnitudes, take the inverse cos, and we find the angle between them. Okay, so let's take the magnitude of A. So when you do this, you take the square root of the components squared. So this is -6 squared plus 8 squared. And this equals square root of 36 plus 64. And this gives you 10. So the magnitude of B, so we take 5 squared plus 12 squared. And this equals the square root of 25 plus 124. Pardon my bad penmanship. And this will give you 13. Okay, so now that we have the magnitudes of the vectors, we now want to go ahead and find the dot product between the vectors. So that all this is we take the component of x multiplied by the component of x of our a vector, then we multiply that by the x component of our b vector, and we do the same for the y's, and then we add them together to get a scalar. So when you do the dot product between two vectors, you actually get a scalar out of it. So we get -6 times 5 plus 8 times 12, and this equals -30 plus 96, which equals 66. Okay, so now that we have our dot product and the magnitude of our two vectors, we can find the angle, so therefore cos theta equals, from above, a dot b over magnitude of a times magnitude of b. And this equals 66 over 130. And when we do the inverse cosine on our calculator, we find that theta equals 59.5 degrees. Okay, so that is how you use the dot product to find the angle between two vectors. Note here, this also works in 3D. Actually works in n-dimensional space, but 3D is enough for this class. Okay, so now that we've covered the dot product, I'm now going to move on to the cross product. So, what is the cross product? So let's say, draw a little something out here. So let's say we have our coordinate system. This time I'll do a three-dimensional case. So we have x, y, and z. And let's say we have one vector e that is just lying along the x-axis. We have one vector a that is just lying along the y-axis. And when we take the cross product of a cross b, we will get another vector here, which will lie along the z-axis. Because when you take the cross product of two vectors, the vector that you find will be orthogonal to both vectors that you're taking the cross product of. And actually, to find the direction of the vector from a cross product, in physics, we use the right-hand rule. So if you point your fingers in the direction of A, curl towards B, you have your thumb pointing up, and that will be the direction of the vector found from the cross product. So I'll write that down. So in physics that's used a lot, but you can also find it through mathematics. So the formal definition of the cross product is similar to the dot product. So we have A cross B equals the magnitude of A times the magnitude of B sine theta. So in contrast to the dot product, and then we also have the direction of the vector found. So this is a unit vector that tells you the direction of the vector found. So above it'd be z hat. So yes, as I said, in contrast to the dot product, this is max when theta equals 90 degrees, because that's when sine 90 equals 1. So if these vectors are perfectly orthogonal to one another, then that's when the cross product is maximized. Okay, so let's do another example here. So what is the cross product of these two vectors? A, which equals 2, 3, 4, B, which equals 5, 6, 7. Okay, so what I do to find the cross product, so A cross B equals, so what I do is set up a determinant, which all of you should have seen in linear algebra. So I set up this determinant here, and then I write 2, 3, 4. So these are the components of our A vector. And then 5, 6, 7. These are the components of our B vector. And then now what we do is we want to take subdeterminants of this matrix. So it's actually called, I believe it's called cofactor expansion. Just give me 1 sec here. Get out the pen. So what we want to do is we want to take this x hat and multiply it by this minus those. So we take this x hat here, we multiply it by 3 times 7 minus 6 times 4. And then what we'll do after that, once we find the x component, then we take the y component and we do this times this minus this times this. And basically what you can do is you cover up this row when you're finding for the x hat, or the x component of the vector. You want to cover up this row here and this row here, and then all you're left with is this matrix here, which you want to find the determinant of. Which it comes down to just multiplying these two together, minusing these two multiplied together. So I'll go ahead and do it just so you guys can see what it looks like. So we have x hat multiplied by 3 times 7 minus 6 times 4. So that's our x component here. And then we put a minus sign for the y. This is just what it comes down to, is you just get a minus sign here. And then this component will be 2 times 7 minus 5 times 4, because we're now covering up this middle row here, and all we're left with is these numbers here and these numbers here. And then we have 5 times 4, and then plus z hat, and then we cover up this last row here, so we'll have 2 times 6 minus 5 times 3. And when we work this out, we get a vector of -3, 6, -3. Okay. So that is how you do the cross product using determinants, which I think is the easier way, because you can just cover up the rows and then find your submatrices. Alternatively, you can just memorize it. Which I don't suggest doing, but if it makes you feel more comfortable, then go ahead and do that. So we have A cross B. So if you write out what I had above, in the general case, so you have AX, AY, AZ, BX, BY, BZ. So if you have just a general vector, then it actually comes down to this formula here. So we have AY, BZ minus BY, AZ, AZ, BX minus AX, BZ, AX, BY. Sorry, I'm just going to move this over. AX, BY minus BX, AY. So you can either memorize these here to find the cross product, or you can use this here, which is the exact same way, except you don't have to do the cofactor expansion here. So notice that in the dot product we get a scalar value, and in the cross product we get a vector. Okay. Moving on, I'm now going to talk about projections. So I'll talk about the scalar and vector projection of vectors. Okay. So let's say, again, in 2 dimensions we have our 2 vectors, A, and let's say we have some vector B. And there's some angle between them. Okay, so if we want to project A onto B, then this is the vector that we want to find. Sorry about that, that should be straight. So this vector here, so this is the projection of A onto B. Okay. So the first thing that we can look at is scalar projection. Okay, so in scalar projection, or the notation I have here is just the component of A onto B. So this is the notation I'm writing down. So we have the component of A onto B, which is also the same as a projection, it's just the scalar projection of A onto B. And this equals the magnitude of A cos theta. So from the dot product, we know that cos theta equals to A dot B divided by the magnitude of A times the magnitude of B. So right away we can get rid of this, and all we're left with is A dot B over the magnitude of B. So really what this gives us is a unit vector of B, because when you divide by the magnitude, you then get a unit vector. and then multiplied by A. And that gives you the scalar projection of A onto B. Okay, so as I said, B over B, so the vector B over the magnitude of B, this is a unit vector, which tells you the direction of B. I'll rewrite that. So this gives the direction of B. Okay, so the vector projection is similar to the scalar projection. So for the vector projection, which I'll write down as this, so the projection of A onto B equals the unit vector of B, so we have B over the magnitude of B times the scalar projection of A onto B, or the component of A onto B. And this simply equals A dot B over B squared times B. So as you can see, the scalar projection will give you a scalar value, because this is a scalar value here, and this gives you a scalar value. But the vector projection will give you a vector. Okay, so now that I've covered some different material regarding vectors, I will now move on to a problem from the textbook. So this is problem 112. So in this problem, we are given 3 points that create a plane, and then we want to find the distance from the plane to the origin, or the height between the plane and the origin. So this example is really good because we actually use the dot product. We used the projection, and we use a little bit of cross product notation, but you don't have to use it too much. Okay, so let's go ahead and just draw this out. So we have a point here, which I'll call C. I'll have a point here called B, and I'll have a point here called A. And then I'll have my origin here. So this is a 3-dimensional system, but I'm just drawing it in a 2-dimensional way. So I'll have my A vector here. So this is A. And then I'll have my B vector here to the point B. So I'll call this B. And then I have my C vector here. Okay, so what we want to do is we want to find the normal vector for the plane, because if you guys remember, for a plane, this is the equation that describes it. Excuse me. So the first step is to find the normal vector from 2 parallel vectors, or 2 vectors that lie inside the plane. 2 vectors that lie inside the plane. And then, once we have our normal vector, we then want to project the normal vector onto a vector that connects the origin with our plane. So I will use the vector A, but you can also use the vector C or the vector B, because they both have a point at the origin and the point inside the plane. Therefore, the height, which again is scalar, which I showed you from the scalar projection. But what we want to do is we want to project the normal vector of the plane onto a vector that's both connected to the origin and the plane. And that will give you the height between the origin and the plane. Okay. So once we found the normal for our plane, we then want to project the normal onto a vector from the origin to the plane. So that will give us the height. There's also an alternative way to do this. You can actually find the volume of the plane and then divide it by the area, but I like this way better. Okay, so two vectors that will lie in the plane that we know for sure are these two vectors here. So b minus a, that's definitely going to lie in the plane because these 2 points are in the plane. And this vector here. Which is c minus b. So we know for sure that these two vectors lie in the plane. Therefore, we can find our normal from it. So normal vector is now b minus a cross c minus b. Because we want a vector that's normal to the plane, so it's perpendicular to the plane. Therefore, to find a vector that's perpendicular to the plane, we want to take two vectors that lie parallel to the plane. Because we know when you take the cross product of two vectors, the vector that is a result of the cross product will be perpendicular to both of these vectors here, both b minus a and c minus b, both of which that lie inside the plane. Okay, so now that we have normal, we can expand it out a little bit. So this actually equals b cross c minus b cross b is just 0, since the cross product of when you take the cross product of two vectors, you just get 0 of the same vector. So then we'll have minus a cross c plus a cross b. So that's what happens when you expand this out. When you expand this out, you get this here. Okay. So now that we have that, we need to find the magnitude of n. So the magnitude of n is just the magnitude of this above here. So we have this. We can't really do much with it, so we can just write it out. So we know the magnitude from this. And then lastly, we have our vector a. So now, as I said, we have our normal. Now we want to project the vector a onto the normal vector of the plane. So the way we do that, which is actually is the height, so we take the absolute value of a dot n. I don't think you need to take the absolute value. We take a dot n, and then we divide that by the absolute value of n. So we take a dot n, so we'll have A dot B cross C from above minus A dot A cross C plus A dot excuse me, A cross B. So immediately we can get rid of two terms here, which is all divided by, and I'm not going to write it out, but I'll write it out after. So immediately we can get rid of two terms here. When you take the dot product, so we know that when we do this, we'll have a vector that is completely orthogonal to A and C. Therefore, when we take the dot product of A, after we find this vector here, we'll automatically get 0. So anytime you see A dot A cross C or whatever arbitrary vector, you know immediately that this will be 0 and this will be 0. Because the resultant vector from this cross product will be orthogonal to this, and therefore the dot product will be 0 from the formula that I wrote above, which has a cosine theta, because cosine theta of 90 is 0. So therefore you'll always get 0. Okay. So then all we're left with is this here. So we have H equals A dot B cross C divided by this guy here, which I'll just highlight. Oh. Why is it not working? Okay, I'll just write it out. B cross C minus A cross C plus A cross B. And that will be the height for a general plane for the origin. Okay. So in the second part of this question, asks you to find the area of the triangle that forms between these three vectors, or these 3 points. Okay. So let's draw this out here. So let's draw out our triangle. So we want to find the area of the triangle that forms from the 3 points. Okay, so we have, again, we have our C here, we have A here, we have B here. So we want to find the area of this triangle here. So we have B, C, A. Okay, and then we have our origin over here somewhere. And then we have our vectors A, we have C, and we have B, which point to our points. Okay. So the first thing we want to do is we want to find the area. So the first thing we notice is that the area of the parallelogram. So if we take this vector here, which is C minus A, and we take this vector here, which is B minus A, I'll call this AC, which is C minus A, and AB, which is B minus A. So when we find the area of this, which is simply the cross product between these two vectors, we'll get the area of a parallelogram here. So we'll get that full area here if we take that cross product. But we want to find half of that. So we simply just divide it by 2. Okay, so the area of the triangle is just the absolute value of the cross product between AC, which is C minus A, and AB, which is B minus A. And then you divide it by 2. Because when you do this part here, we get the area of the parallelogram rather than the area of the triangle. So we divide that by 2. Okay, so when you do this, so I'd write it in the form of the vectors that are given. we get C minus A cross B minus A. And we divide that by 2, and this will be the area of that triangle. Okay, so that is it for this tutorial. I hope everything made sense. So just a recap, I covered a little bit of vector notation, the dot product between two vectors, the cross product between two vectors, scalar and vector projections, and then I did an example which included dot product, cross product, and scalar projections, which was nice. Okay, see you guys later.